Almost got that on the video. Okay, here we go. We are going to do good old-fashioned lecture. Oh my goodness. Chapter 8. The title of the chapter is Haloalkane. Now, in nature, there are not many haloalkanes. To date, maybe several thousand have been discovered. I mean, that's, in nature, that's like zero. Okay, it's not like they don't exist. One main reason is they don't exist in nature is because they're reactive. So even when they're made in nature, they've done something already and the halogen departed. Why did the halogen depart? Because halogens are good. What's a synonym for departing? Leaving. I think I was getting an Arabic translation. How do you say leaving in Arabic? Let's say it again. Pada? Rada. Okay, it's okay. We'll do all again. Anyway, I'm sorry. We're getting a little more than chemistry here. Haloalkanes, they react if they're made in nature. Some do exist in nature. I think there's several in the textbook listed. But we use them in lab a lot. So when we want to mimic what's going on in nature, halogens provide us a way to do so. In nature, the best leaving groups are often phosphates. Okay, working with phosphates in lab, we haven't mastered what nature has, and it's just they're temperamental. More predictability with things like haloalkane. All right. So the mechanism that we're concerned about in this chapter is some kind of halogen molecule. So bromine and chlorine are the two most popular. Iodine. Let's avoid fluorine in keeping with our tradition of avoiding fluorine because it does a lot of things. Generally, it'll do some of what you want, and there'll be a whole lot of other stuff going on too because it's so reactive. So we'll just do ClCl for now. And these reactions, what gets the ball rolling is energy in the form of either light or heat. So the generic formula for energy of radiation of any variety is H nu. And H nu is heat. Now, you know what radiation is heat? Say it again. No. Oh, no, don't be cooking with gamma particles. There won't be anything left to eat. Okay. H is heat is infrared. Or light. One of the colors of light. And what happens is you'll get this as major. Any surprise that that's major and this one is minor? I bet there's no surprise. Although we're not talking about an alkene reaction, right? It seems to be a substitution issue, doesn't it? The Markovnikov one, I didn't move the Cl. There we go. Okay. And the other product is kind of important here. Even though it's a side product, oh my goodness, it disappeared. Yeah. Black H, blue Cl, and I'm going to recolor my Cl's blue. Don't make my Cl's blue. And there you go. And this is a very different mechanism. Very. What the heat or light does is it pops open the weakest bond on the page. And the weakest bond on the page is the weakest because it suffers from lone pair repulsion. With the only atoms that have lone pairs bonded to an atom next door that also has lone pairs. ClCl. So what happens is, in the presence of heat or light, depending on the reaction being studied, heat or light starts the, and it's a good name, initiation, init, good short form, reaction. And here's your ClCl. Here's your H nu. And here's the result. And this is something new. And because it's something new, I'm going to show all the valence electrons. You don't have to, but I just want you to know that you've made a chlorine that's got 7 valence electrons, like the one on the periodic table. Yeah, and this is why chlorine doesn't like being chlorine without another chlorine, because it's got an unpaired electron. And that's called chlorine with an unpaired electron, has another name, starts with an R, ends with an L, radical. I was going to give you more clues with politics involved and stuff, but let's not go there.
That's why they use chlorine and bombs, because it affects the water.
No, they use chlorine in bombs because chlorine creates chlorine water when reacted with water, which is very reactive towards alkenes. We've studied that reaction in the lungs, yes. And it reacts with the moisture in your lungs, creates HCl, and it also chlorinates alkenes in your lungs, and it's terrible. Chlorine's nasty. Chlorine with heat, even nastier. So your chlorine radical is there, and it's reactive. You can turn your light off now, or your heat. You just need to make 1 or 2 of those. You don't have to react all your chlorine this way. In fact, less than 1% of the Cl2 reacts this way. But you have to show this reaction because you need a start for your chlorine radical so that you can do the next reactions and the cycle will start. And yes, the next 2 reactions are in a cycle, and they got a good name too. Propagation. Have you ever heard the word propagation?
They use it for grass.
For the who?
For crops. Propagation.
That's crop dusting.
They don't say like propagation system.
Maybe. It's not a context in which I'm familiar. I'm sorry. But in biology, I know what propagation is. The species will propagate itself with biology, right? It keeps itself going by reproducing, right? Well, that context is exactly the same here. I'm going to use that chlorine radical and what it's going to do, I just noticed I didn't do the mechanism for that step. I lost a point on my own test. So before we do the propagation step 1, the mechanism above is fascinating. The heat causes the bond to pop in half. So you tell me what these curved things are, and don't say arrows. They're not. They're called hooks. Hook, H-O-O-K. Hook equals 1 electron moving. One electron. That makes sense, right? Arrows have the double head, and that's 2. So now this hook is going to meet this hook, and the other half is going to go on to the more substituted carbon there, see? I like to call this, and you might not like it, but it makes it easy to remember. It's called a hookup. Because the H hooked up to the Cl, right? And you generated a carbon radical. Carbon radical. I think it's our first carbon radical, isn't it? Mm-hmm. It has no formal charge. If you want to do a little look-see at the carbon radical, it's a C that has an H and a CH2, CH3, and a CH3 and a dot. Do the formal charge calculation for me. It owns half of that, half of that, half of that. That's 3. It owns the whole electron here. It's called the radical, right? That's 4. Carbon on the periodic table, what group? 4. It's got no formal charge. It's got that going for it, but it's got an octet violation going against it, which is severe, right? Octet violation, it can never be made into a good story. You've got to fix that before your reaction's over. And we're going to do that now. Moving this picture away. Can I short form this to Prop 1? Hey, we got an election tomorrow. Prop 1, Prop 2. Don't forget to vote tomorrow.
Randall, you get extra points if you vote.
Points. About points. He's right there. Hey, he beat me to the punch. Maybe in the future, huh? So we got this carbon radical. And we got ClCl. And more than 99% are going to react this way. And it's another hookup. Carbon grabs Cl. I hope that looks like the one above it. I hope it looks a lot like the one above it. Bless you. And you have made the other product from the top of the page. Bless you. Whoa. There we go. And we got a blue Cl. No, it's blue. You don't like that? And this, oh, that's the most interesting thing to me right there, that ends thing. Because guess what Cl radical is going to do now? That's chlorine radical, right? Yeah. What's it going to do? It's going to go back here and grab a second molecule's H and make these two. And then this guy is going to grab another chlorine from a new molecule of Cl2 and make these two. And then this guy is going to come back and do this again. Do you see it being a cycle, everybody?
So always HCl. That's what it doesn't look like. HCl.
Yeah. This reaction, this is a different reaction than the one hurting your lungs.
That's how I remember it.
Yeah. There's some similarities, but that's not the chemical warfare agent. Chlorine doesn't have the heat or light, so it's more like the chapter 6 chlorine, and it reacts with alkene. And this one's a radical reaction. And we're making this. So these two are cycles. And I'll prove it to you. Prop 1 plus Prop 2. I want it below this line. And some of you may have studied this and some of you haven't. There's a name for a reaction where a species is made in one step, and then that same species is used in another step. There's a name for that species. It's not a product. I know it's a product of Prop 1, but it's also a reactant of Prop 2. So it's there and gone every time. Use it, make it, use it, make it, use it, make it, use it, make it, until all the chemicals required to make that thing are gone. All right? So what do we call those species that are made in the middle of a reaction and then converted to something new? They're intermediates. Yeah. and intermediates that are made, and intermediates, the same intermediates are reactant, in the overall reaction, you're not going to see them. They're used up. Yeah. They're important in the mechanism, but you don't see them at the end of the reaction. They're just not there. So this cancels this, and the chlorine cancels the chlorine. Everything else stays because it's only one time. Butane's one time. And I'm really wasting my time doing this because I'm copying what's on the top of the screen, which you can't even see. But you have it on your quiz. No, you don't have a quiz. I forgot. We're not doing a quiz. Yeah. Rondella wants points. Rondella.
Can I do a signing sheet so we can?
She's still working. She's trying to help me now. She's so helpful. Okay. No, don't worry. I got something for you guys.
10 push-ups.
10 push-ups. Okay. So what we're going to do is, can you copy the mechanism only without any words, which you probably have done already, on a new piece of paper? Take your time. Do you still have one of my activity? Oh, please flip it over. This is perfect. Flip it over and copy the initiation and the 2 prop steps. You do that now while I pause the video. Good luck. I'm hoping this works, everybody. We had quite a long pause there. We decided during this long pause some good things. Well, I think they're good things. Starboard, we're here. We decided we're going to use as our study guide Fall 19 T3, except, yes, part 1, number 19, and just a reminder, IHT. And part 4, number 8. Molecular recognition doesn't exist anymore. Layout. Okay. And this is the BDE table. Example. That's the reaction, and the table is homolysis, a good name. It says take a bond and break it evenly. That's your hooks. These are your hooks. And the thing that caused that was the H nu. And I'm going to tell you, in this specific example, the amount of H nu required was exactly 357 kilojoules for every mole of bond you broke. The reason is the category of carbon bonded to hydrogen. Category. Now, right now, you're going to just say secondary based on your knowledge now. But we have to add a word because it's not just secondary. I agree with you, it is secondary, but that's not the most important part of this story. Because this thing can resonate, unlike a normal secondary carbon, and please convince yourself those hooks lead to this resonance structure. It's a resonance stabilized radical because it's blank radicals are resonance stabilize. We need a name for a radical that's doing this resonance. And its name is based on this group. What's this group called? If it was a nomenclature question. Allele. Allelic radicals are resonance stabilized. What makes something allelic? It's on a carbon adjacent or vicinal to an alkene. Any carbon adjacent to a alkene is called, what kind of carbon? Allelic. It's not just a group, it's a chemistry. It puts you in a family of related chemistry. Okay? That's why we need to add the word secondary and allelic and get 357 instead of just secondary. I'm going to go for another color. Secondary is this one, believe it or not. This one is secondary. This one is secondary. Allelic. Big difference. Huge difference. 45 kilojoules. That's about a 10% difference. So you think this allelic's important? You better believe it is. Yes. All right. Now, I've got another question. What about this? So say I had this guy right here, and it was doing this. And it's reacting with H dot. Isn't this the opposite? They're hooking up. They hooked up. Here's your H. Can you give me a, this is delta H, by the way. What is it for this one? I want a number. Oh, she's good. She started with a negative sign. Why? Because if a forward reaction is endothermic, the reverse reaction is exothermic. But the better why? The better why? Why is it exothermic? Well, because anytime you answered that question, you can see if you get away with this answer, because there's nothing wrong with this answer. It's exothermic because it got more stable. But you know the teacher's next question. Why is it more stable? You made a bond and got rid of two species that had octet violations. You better believe you're more stable when you're finished getting rid of octet violations.
This is one of the first time we did it based on this on the tertiary.
Yeah, because we've been doing mechanisms up our wazoo until now. He says the first time we haven't been talking about secondary, tertiary, and stuff like that. Although it is related, right? But delta H here is negative, and I need a number. And don't give me 2, 3, 5, 7. It's not the same category anymore. Give me a category for this CH bond. Don't tell me it's secondary at all. Tertiary. What do you call it when it's on a carbon adjacent to an alkene? Allelic. And I want to go with negative 354. Don't you? Why? 54. I said it and I didn't write it. kJs per mole, right? Well, where's the 354? Let's highlight it in baby blue. Highlight it first. Haven't used it. I did use baby blue. Never mind. Hot yellow. Where's the 354? It's right here. Why did I pick that number? Tertiary allelic.
Because of the sp3 there.
Because the carbon has 3 bonds to carbon is why it's tertiary. The carbon has 3 bonds to carbon, that's why it's tertiary. It's allelic because it's on a carbon 1 away from an alkene. There's 2 parts to this name, there's 2 parts to the explanation. And I just want to point out, these are similar in terms of the numbers going down from the top numbers. Has a similar effect, but these are all called benzylic. Notice I did not pick the first one right above it. Primary, secondary, tertiary. This is phenyl. Please don't break phenyl bond to H. Why did I just say that? Please, on your any test, don't break in half a phenyl bonded to an H. What's the reasoning? I just want you looking at the number. Maybe the numbers are small up there, and I do know that. But look at all the numbers we've used so far, and now you're going to break a 464 before a 357? No. Weaker bonds break first. Okay? Stronger bonds break last. The stronger bonds don't break at all. How's that? So you're always going to have a number less than 464 to choose, is what I was saying. Please don't choose a big number. Okay, so we got a good intro. And before we finish our intro, what does homolysis mean again? Breaking in halves evenly. As opposed to our mechanisms until now, haven't they involved a pair of electrons going towards one atom and then a pair of atoms leaving towards another atom? That's heterolytic, isn't it?
The only one with ozonation was a little different.
A little different, that's right. But it had the arrows like we've been doing now. It's hook time, right? Okay. And I want to ask you the question, why is this one endothermic? Because the two species you're making are, well, let's see. We got your, I got reactants, I got products. This is backwards to your visual right now because I'm doing it for my visual. All right? I could turn around and stuff, but reactants and products in an endothermic reaction, right? The products are less stable. Reactants are more stable. Why are they less stable in that positive 357? Because you're making octet violations. Makes sense. Go in the other direction. You start off with radicals, and we're going this one. Start off with radicals and make full octet. So you're starting off high, ending low. That's why it's exothermic. Species got a lot more stable. No, don't worry about that. No, do worry about that. That's okay. But I'm always hesitant right now because some of you are taking 142 and you're learning about this guy, and when you have these reaction cycles with multiple steps, this one's, I think it's a German name. And there's an author with the same name, Hermann Hesse, who wrote Steppenwolf and Siddhartha. And this one, Hermann Hesse, is not the chemistry Hesse. But please, don't talk about Hesse. Here's your Hesse replacement. You ready? Your life's easy, right? Make life easy, and then life's easy. Breaking bonds is endothermic. Fact.
Breaking bonds.
Well, think about it. Things are bonded is what's holding them together. They like being this way. How are you going to get them apart? Are they just going to happen on their own? Or are you going to yank them apart? Dude, they're held together. This green thing is held to this thing. What's the only way to get them apart? I've got to put in energy. Right? That was endothermic, right?
So in the ice pack.
Now, if I just drop this on here on a perfect angle, it doesn't need me doing anything, right? It's not going to happen. There. I really didn't do anything. I just wanted to be there, right? Okay. So what kind of reactions are exothermic?
Connecting bond.
Connecting a bond. Exactly. Nicely said. So breaking endo, making exo. Well, hey, bonds makes the electron more stable. That's exothermic, right? You make a new bond that wasn't there before, these electrons just got happier, more stable. Okay, that's all you have to remember. Now you don't have to remember anything about the words products and reactants. You just forget all those words. When Bella was going there, I know she was. Yeah, because she knows a little bit of stuff. Okay? How are we doing on time? We're doing okay.
Okay, so the first one is homobites.
Well, yeah, and this is homogenesis, I guess. I've never even heard it used. Homogenesis? But normally in biology, that's making of mankind, right?
Because we have life,
The opposite of cutting would be making, right? So that's why I threw I made that word up, homogenesis. But you can use it, feel free. And yeah, I think we'll do a quick video on using this on a test question. But that'll be the next video. So did you